Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about eigenfunctions and eigenvalues. And essentially in this video I want to define what an eigenfunction and eigenvalue are. And the reason why we want to study eigenfunctions and eigenvalues is also because they're fundamental to the Fourier series, as we will see. And I have made a video on the Fourier series in the past, which I will post in the top right hand side corner of this video. So please feel free to check that out. And they're also fundamental to the Laplace transform, which I will make a video of in the future. And to interpret this function here, we can say that given a system H and an input x of t, if I input this x of t into my h, and what I receive is again this x of t and some complex constant lambda, call this a, e, j theta, then I can say that x of t is indeed an eigenfunction to my system H, where lambda is the eigenvalue. Throughout this video, I'm going to reiterate the definition, and I'm going to give many examples to really drive home the point of eigenfunctions and eigenvalues. Okay, to have a clear, concise, written definition, we say that an eigenfunction x of t of any arbitrary system H is a function that satisfies y of t is equated to my system H times my input x of t, which is also equated to lambda times my input x of t, again where lambda is some complex constant a, e to the j theta, which we call an eigenvalue. So this here is a written definition. And as a side note, I want to say that this system H has a selected number of functions x of t that are eigenfunctions. All right, so h of t only has a selected number of x of t. Another way to say this is that not all functions or input x of t are eigenfunctions of this arbitrary system H. So let's make sure to understand that moving forward. Okay, let's go ahead and take an example now to really show what this eigenfunction and eigenvalue really mean. So in this example, it tells us to find if the input x of t is an eigenfunction of my system H, where h is the second derivative and this d here is the derivative operator. And I want to consider two cases. Case A is when x of t is cosine of t, and another case is when x of t is equated to t cubed. So if we consider case A, pictorially, this is saying that imagine if we have x of t is equated to cosine of 2t, and this enters a system H, which is equated to d squared over dt squared. It's asking us to see if this x of t is an eigenfunction of this operator h. So in order to find that, we need to satisfy our equation. So we say that y of t is equated to my system H of x of t, which is equated to d squared over d2 squared times cosine 2t. Let me go ahead and call this equation number 1. And now what I need to do is complete this operation to see if I can simplify y of t to be my input x of t times some complex constant. So I say that y of t is equated to h times x of t, which is equated to d squared over dt squared cosine of 2t. This is equated to d over dt minus 2 sine of 2t. And this here is equated to minus 4 cosine of 2t. which I can say is equated to minus 4x of t, or simply put, I can say is lambda times x of t, where this lambda is equated to minus 4e to the j times 0. So as you can see here, this e to the j times 0 is just 1, so I can get rid of it, and lambda is just equated to negative 4. Let me reiterate and say again that this x of t is indeed an eigenfunction of this system H, because it has an eigenvalue, which is a complex constant, right? Minus 4. Again, e to the j times 0, which I will not write. But I hope that makes sense of why x of t is indeed an eigenfunction of my system H. Let me go ahead and call this equation number 2. Now I'm going to write out a key point to eigenfunctions and eigenvalues. But what I want to do first is point out what's going on here between equation 1 and equation 2. Specifically, if you look at equation 1, we have this derivative function, which we have to compute every single time. So imagine if every time someone gave you a value of t, you had to compute the second derivative of cosine of 2t before finding a value. That would be very tedious. Versus if you were to look at equation number 2 here, and every time someone gave you a value of t, all you had to do was multiply it by this negative 4. And essentially, that is the beauty and the take-home point here for eigenfunctions and eigenvalues. If you find the eigenfunction of a system and its corresponding eigenvalue, it physically swaps out calculus, which is a differential, integration, or convolution, for arithmetic, which is things like multiplication and division. And essentially, arithmetic is preferred, or a preferred method of doing mathematics compared to calculus. And this is the main reason why we care about eigenfunctions and eigenvalues. If you have any questions on this slide, please leave them down in the comment section below, and I'll be sure to get back to you. And before I go on and do part B of my example, I want to really highlight the key point. So I've written it out clearly, so feel free to pause the video, read this on your own time, or follow along as I read it as well. And the key point to eigenvalues and eigenfunctions is that imagine your system H was not a clean second order derivative like we had in our example, but an aggressive fourth order integral differential equation. Then y of t is equated to my system times an input would be very complex to complete. Essentially, having to solve this complex equation for every input of time t would be very, very tedious. But if we can simplify y of t by finding out the eigenfunction, and we do this again with that input x of t, if we just input it into our system H, we can find out if it's an eigenfunction of the system H and the corresponding eigenvalue associated with this eigenfunction. Then the solution y of t is equated to lambda x of t becomes a more simpler or straightforward problem. And if there's one thing I want you to take from this video, it's this point right here that says that eigenvalues and eigenfunctions allow us to leave from calculus and go to arithmetic. All right, that's the number one thing. And this is to simplify the solution or the output y of t of a system. And lastly, this incredible simplicity is the core reason we care about eigenvalues and eigenfunction. All right, so if anyone were to ask you what is the purpose of eigenvalues and eigenfunction, the core reason is to go from calculus to arithmetic. Instead of solving integrals and derivatives, we rather solve multiplication and division. and eigenvalues and eigenfunctions allow us to do this. I hope this makes sense and this description was really helpful. If it was, please let me know down in the comment section below. So the second part of our example, or part B, says that imagine x of t is equated to t cubed. Again, we said that not all function x of t are eigenfunctions of a system. So what we do is we're going to go ahead and plug this in to my system. And we said that my system was this h, which is d squared over d2 squared, or the second derivative. And my output is y of t. So we can say that y of t is equated to my system h times x of t is equated to dt cubed over dt. Again, this is similar to my equation 1. Let me call this equation 3. And y of t is equated to h x of t, which again is this dt cubed over dt, which is simply just d times 3t squared over dt, which is simply 6t. We can go ahead and manipulate this 6t here to be equated to 6t cubed over t squared. So then what do we get? We get 6 over t squared x of t. And if we say that this is equated to lambda times x of t, where again this lambda is equals to 6 over t squared, this here is not a complex constant, right? Obviously it's not a constant, right? So t squared is not a constant, it's a variable. So that means that since lambda is not a complex constant, this input x of t, or this function x of t, is not an eigenfunction of my system H. I hope this makes sense, and I hope we now understand the idea of eigenfunctions and eigenvalues. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and classmates so they can also obtain the knowledge given in the video. And lastly, if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.